All right, let's talk about Turing machines. So I want to talk, this is a bit of terminology that we haven't talked about, and then some things to say about it. The category of languages associated with Turing machines. Everybody knows finite automata, the NFA and the DFA, those correspond to the regular languages. And then we also have the category of context-free languages, which have context-free grammars. The languages associated to Turing machines, here's so just sort of simple terminology here. So if M is a Turing machine, then we let L of M be the language of M. Language accepted by M, as usual. And this, as usual, it means all the strings which are accepted when you plug them into this Turing machine. This is the set of all strings which are accepted by M. Right? And remember, for a Turing machine, accepted means you start with this string on the tape, run the machine, and if the machine ever enters an accepting state, then the string is accepted. All right? So L of M means the set of all strings which are accepted by M. And really what I would like to talk about is the collection of all the languages which are of this type. And that has a name. Unfortunately, the name doesn't have the word Turing in it. If L is the language accepted by some Turing machine, this is a somewhat weird name, then L is called recursively enumerable. Recursively enumerable, which I'm always going to write RE. All right, that's the name for the languages which can be accepted by some Turing machine. It is called recursively enumerable. This bit of terminology, if you recall what I talked about, something I talked about last time was that Turing invented this whole discipline, but actually there was another guy, Church, who also invented sort of an equivalent system, which we now call the lambda calculus. I believe this terminology comes from Church, so he used different words for everything, but they were all equivalent to the same stuff that Turing was talking about. And this terminology, recursively enumerable, makes a little bit more sense in Church's model. But anyway, that's what we call it even in the land of Turing machines. These languages are called recursively enumerable. That is RE. Another way of saying this is, I'll just say IE. This category of languages, RE languages, are those for which, as we discussed last time, the existence of a Turing machine is equivalent to the existence of an algorithm. In modern terminology, or in modern language, we call these things algorithms. Usually nowadays when someone says algorithm, they usually mean specifically like a computer program that you could write in a programming language, but those things are all equivalent to Turing machines anyway. So another way of saying this, like when your friends ask you what does RE mean, you could say it means accepted by a Turing machine, or you could just say these languages are those for which there is an algorithm which accepts X if and only if X is in the language, right? I should say L up here. When you say L is recursively enumerable, it means there is an algorithm where I give you X, and if X is in the language, then it's accepted. And only the ones which are in the language get accepted. That's what this if and only if mean. All right, so as we go on, I'm going to use sort of the word algorithm as a stand-in for there exists a Turing machine which does this or that. All right, from a modern sensibility, that's what the word algorithm means. It means there is a Turing machine that does whatever it is you're talking about. All right, so that means this is sort of this diagram, this hierarchy of languages, which I wrote, I don't know when the last time I made this little diagram was, but it was a while ago. You have the regular languages are kind of like the most simple and most restrictive type that we've discussed, and then you have the context-free languages. Those include things like A to the N, B to the N. And then the next larger category are the RE languages. These are the ones which are accepted by a Turing machine. All right, Turing machine, of course, is more capable than a context-free. And then there's even stuff out here that we will discuss, although we don't have all that much more time in the semester, but we are going to talk eventually about stuff even outside of this RE class. But for today, we're just going to focus on RE mostly. What I would like to discuss for a moment, how about some closure properties in the RE class? That is to say, if I have two languages which are RE, what can you say about their union or their intersection? That kind of a thing. This is something we talked about for regular languages. Actually, we didn't really talk about this for context-free languages just because I didn't want to take up time on it, but I would like to talk ever so briefly about it. So closure properties in the RE class, that is to say, if I have, say, L1 and L2 are recursively enumerable, then is L1 union L2 recursively enumerable, or L1 intersection L2, etc.? Right? Those are the kinds of questions that I would like to ask. All right. And maybe you can we just think about, informally speaking, do you think that the answer here is yes? Like, for example, L1 union L2. What this says is, if there's an algorithm to decide if something is in L1, and also an algorithm to decide if something is in L2, is there an algorithm to decide if something is in L1 or L2? Any thoughts? I see some nodding. I feel like if you know how to tell if something is in L1, and you also know how to tell if something is in L2, then yeah, you should know how to tell if it's in this one or this one. You just do these two things and combine the answer with a or. All right. So I'm going to try and write this out slightly formally, although not super formally, but I'm going to write this as a theorem. And I will say if L1 and L2 are RE, then L1 union L2 is RE. All right. I'll write this like a proof, although you'll see I'm going to be not super technical about the proof. You know, if you really wanted to write this proof very technically, you would do it on the level of Turing machines, but I'm going to just talk about algorithms. All right, so we assume, in order to make this argument, I'm going to have you guys try and do the intersection. It's going to be almost the same, and then there's going to be some more variations on the homework. So let's assume that L1 and L2 are RE. That is, and then we'll show L1 union L2 is RE. All right. So what does our assumption mean? This means there are algorithms, and maybe I'll just give them names A1 and A2. I'll write my fancy A. A1 and A2. All good mathematicians have a fancy font, which we can use when called upon. My fancy A just has a little extra fancy business over here, right? So that means there are algorithms, A1 and A2, which accept, well, maybe I'll say where A1, the algorithm A1 accepts X if and only if X is in L1, and A2, the other algorithm, accepts F if and only if X is in L2, right? That's the point of those algorithms. So there is some way to tell that X is in the first language, and there's also some way to tell that X is in the second language. Now, our job is to demonstrate an algorithm or describe an algorithm which tells you how to tell if something is in the union. But this is not so hard to do, so I will just say here is an algorithm which accepts x if and only if x is in the union. I would say, and there are a lot of ways you could say this, but I would say you basically start with x, you do both of these algorithms and see what the answer is. And then when it's accepted in the, you just like do the OR of those two answers, right? That's the idea here. So given input x, I'll write it in this way. Given input x, run both A1 and A2 on it. And then if either one accepts, either or, then our new algorithm accepts x. That's it. All right? So this will accept x when it's in this one or that one. Yeah?
So for DFAs and NFAs, we were able to draw a diagram for the intersection and union of
right.
them.
Yeah.
Are we able to do the same here? Or
It's not so easy. Yeah. So in the case of NFAs, you have this sort of various tricks with epsilon transitions in the diagram. It's not so easy to draw. The idea would be if you start with two Turing machine diagrams, you somehow combine them together with arrows. And that is, in theory, possible, but there's not like a simple, just put an epsilon here, because you have to manage the tapes and all that. Yeah. It's more like in terms of Turing machines, this is more like starting with two Turing machines, which each have their own tape. And then this algorithm as a machine, I would say, is easiest to express if you express it as a Turing machine with two tapes that's doing two separate things on each tape, which is fine. That is allowed and that does exist, but it's not an easy thing to write in terms of the diagram. Yep. All right, great. Then our new algorithm accepts x. And so this one accepts, so because of how I did it, x is accepted if and only if x is in the union. Because I said, if either one accepts x, then our new algorithm accepts x, right? That's how it goes. All right, could we say the intersection? What do you think about the intersection? I was going to ask all of you, but maybe we could just sort of talk this through, because I think the modifications are very minor. How would you change this argument here to make it work for the intersection? Any thoughts? What do you think?
Union to intersection and
yes.
Either one to both.
Yeah, right. The only difference really is, of course, you would write all these unions as intersection signs, but the real difference would be just right here. If either one accepts x, you change this to if both accept x, then the new algorithm accepts x. And then you get the union. So I will just say to get, then you get the intersection, right? Really, everything is the same except you change either one to both. All right? And everything else works the same way. Great. So the RE category of languages, it is closed under unions and intersections. What about, and this is something that we also talked about for the case of DFAs and NFAs, what about complements? So how about complements? This one would seem to be simpler on its surface because a complement is something you just do to one set. That is to say, if L is RE, then is L bar RE? That's the question. If L is RE, that is to say, if you have an algorithm that tells you if something is in L, then can this somehow be reworked to create an algorithm which tells you if something is not in L, right? That's the idea here. If you know how to tell that something is in L, is that the same, or can you use that to be able to tell if something is not in L? That's the difference here. This, when you try to write out the argument, you run into a problem here, which is actually very important in what we're about to talk about. So I'm gonna put this sort of in brackets. Actually, what I'm about to write here is gonna be a big dead end. So this is not a correct proof, but here is the natural strategy to try if you wanted to prove this, right? We would assume we have some algorithm, you know, fancy A, which accepts if X is in L, if and only if X is in L, right? And then you would want to do this, but sort of the opposite or something. Now, what I set up here was, given input X, run them both, and if either one accepts, then our new algorithm accepts, right? So what I would say here, to do the same idea, given input X, run algorithm A on X, and accept if A does not accept X, right? Because the whole point of this is that my new algorithm is supposed to be the opposite. It should say, it should be accepted when the string is not accepted in the original language, all right? Run the algorithm A on X and accept if A does not accept X, all right? There is actually a problem with this. And this is, it seems like a small technicality, but it turns out to be a huge deal. Anybody have a feeling about this problem? The idea is, if I want to know if X is, or my new algorithm will just run the old one and wait and see what happens, if it was accepted or not, and then I just kind of like say the opposite in my new algorithm. Yeah? What can you say? Yeah, what if the machine runs forever? This is, certainly it is a possibility for a Turing machine to run forever. This is a big issue for this though. Here, if A does not accept X, all right? Actually, this right here, this is not possible to know even if we have a Turing machine for this algorithm A. Why is it not possible to know? What she said, maybe it runs infinitely, all right? Now, if the machine really does run forever, then that means the string is not accepted, because accepted means it goes to an accepting state and stops, right? So if it's true that the machine runs forever, then this string will not be accepted. The problem is, you can imagine if you had such a machine, while you're standing there waiting for it to finish, you cannot tell the difference between, is it running forever or is it just taking a long time and it's not done yet, all right? So in practice, like in real life, if you're actually trying to work with algorithms or with real life machines, it is not possible to know if the machine is running forever versus if it's actually just taking a long time and about to stop. And this is actually, like, I'm sure that you've all been in this situation when using a real computer. When your computer seems to be frozen and you're like, am I gonna turn it off and turn it back on again because it's really stuck? Or should I just wait a little bit longer and maybe it's not actually stuck? This is because you as the user have no way of knowing if the computer is frozen because it's well and truly frozen forever, or if it's just being really slow at the moment, all right? This is not possible to know even if we have a Turing machine for A. So the issue here is that the real issue is about, the issue is halting. This is the word that we use for this. It's a fact that a Turing machine on some inputs might not halt. And what that means is, so if X is not, well, can I say, well, I'll say it in this way. If the Turing machine or the algorithm runs for a long time. We can't tell if x is accepted or not. Right? Because it may be, while it's running for a long time, maybe that actually it's about to finish and tell us that it is accepted. And you can never know, because a Turing machine in theory could run forever, and you would have no way of knowing the difference. All right? This is a big deal, and it means actually that for this, in terms of being a real life, like useful computational thing, these things in the RE category are actually a little not great, I would say, because things in the RE category, they might actually run forever and you would never be able to tell. So if you were trying to use one of these machines to answer a question for you and it just seems to run forever, this is a bad machine for you to use. It doesn't mean that the answer to it doesn't mean your string is rejected. It just means you don't know the answer. This is a big problem. Anyway, let me give I got a real example of this, and then we'll talk about some more terminology here. So let's try. Here's a very specific example of a Turing machine where this comes up. I got that BBL here. PBR here, accepted. All right. Let's try to think about this diagram. I want to know what are the strings which are accepted, what are the strings which are. There's actually kind of three categories, right? So there's accepted, there's also rejects and halts, and then there's also runs forever. All right. So if the machine just like gets stuck somewhere and stops, that's one category, but if the machine runs forever, that's another category. Anyone want to suggest? Can you say what are the strings which are accepted here? Or any?
Never mind. Sorry.
Can anyone say what strings are accepted? Yeah.
Is it A, B to the M, B?
I wasn't going to say that. I think maybe you're reading this as a R, but this is a L, which changes things a bit. Yeah.
It only accepts B.
B. So B is definitely accepted. You would, as soon as you start, you immediately go here, and that's it. Actually, there's more than just B will be accepted. B to the N would be accepted. You see the B at the beginning, and it's accepted. Actually, if there are more B's, it'd still be accepted because the machine doesn't even go anywhere else. Actually, there's even more. Yeah. B followed by A to the N? Yeah, so B and then some more B's would be accepted. Also B and then some more A's would be accepted. Nobody's saying it in the most generality. BX, yeah, if it starts with B and then has some other stuff, it will automatically be accepted, right? Because the machine, right when you start, if it starts with a B, it goes here, and it doesn't matter what else was in there, it's going to be accepted, all right? So this one here, so if this machine is called M, so here, the language of M is BX, right? Where X is any string, AB star. It's just any string that starts with a B, all right? Those are the ones which are accepted, all right? What about the strings which, and there's two other categories. There's the ones which are rejected while halting, and then there's the ones which run forever. So I'm going to write those as R and F. R for reject and F for like forever. So these would be the ones where the machine halts and rejects. So that would be one in which the machine just kind of like gets stuck somewhere. Does anybody see how this machine could get stuck? Maybe somebody else. Thank you for your... How could the machine get stuck? Just give me one example of a string where it gets stuck. AB. AB? I don't think it's stuck on AB. If you see A first, you go here. And then you see B, it'll come back here. Yeah, like, could we write down what happens with AB? Maybe I would, can I write this? the old school way like this, right? 1, when you see A, it moves to the right and goes to state 2. That would look like A to B. And then 2, when you're in state 2 and you see B, you do the BBL, which means it leaves that as a B and goes back to the left and becomes state 1 again. So the next would be 1, A, B, like that. And then what happens next? Well, that just goes on forever, right? The next step, I'm back where I started, and it's going to do the same thing again. So next it'll be A2B, and then 1AB, etc. So actually, this is one string in which it will run forever. That goes in this category. Can anyone say something in here? Yeah? AA. Yeah, AA is one where it'll get stuck. You do A first, and then another A. There's no outgoing A arrow here, so it gets stuck. And I think that's kind of the only way for it to get stuck, although for the same reason as this, it could have AA followed by some other stuff that it would just never get to, but that would still get stuck just because of the AA. So I'm going to say this part, R of M, these are the ones where it rejects because it gets stuck, so the machine halts and rejects. This, I believe, is AAX, where X is an AB star. And I suppose the empty string also makes it halt immediately. So I would also put the empty string in this little technicality. I also put the empty string in this category because the empty string makes it halt right away. All right. And then what about this FM? That would be the strings which, oh, and also I should say also just A makes it stop right there, right? And not accept it. So this, another technicality, this should also include just A. All right. But anyway, the forever, that would be this, A followed by B. And actually, if you think about it, no matter, there could be other stuff afterwards that just, it never gets to, but it's going to run forever on anything which begins with A followed by B. So this is A, B, X. X is an AB star. All right. So this, those are like the 3 different sets associated with this Turing machine. The first one is still called the language of the Turing machine. The other 2 are, well, they're the 2 different ways that a string could not be accepted. All right? All right, so there is a big deal about this halting business. So in real life, IRL, computers really, I would say, are only useful if they halt. Useful, I mean, in terms of like answering questions. If you have a mathematical calculation that you want the computer to do, or anything that you're trying to get it to do something, it's not helpful if it runs forever and never gives you an answer, right? And even like just because it seems to be running forever, you can't deduce anything from that. You can't deduce that it actually will in fact run forever. You just don't know. So computers are only useful if they halt. What that means is, in terms of real life computation, actually the RE category is kind of too big because this RE category contains even algorithms which might never halt. And those things in real life, we don't want to use such things. So actually what people care about in terms of real life computation is a smaller category than this. And this is, so here's another definition. This is another category of languages. We say if M is a Turing machine, if a Turing machine M always halts for all inputs, this is like the good kind, all right? It means there's no funny business. When you ask this machine a question, it always tells you the answer. It never just like thinks forever or something. So if a Turing machine M always halts for all inputs, then there's a name for that. Then M is called a total Turing machine. Total Turing machine. I think the word total kind of refers to the fact that if you think of this M as a function where like you give it something and then it gives you an answer, total means it always gives you an answer. There are no inputs where it just like never tells you the answer, all right? So if you think of it as a function, That's sometimes called a total function rather than a partial function, which only gives you the answer sometimes. This always gives you the answer. So the M is called a total Turing machine in this case. And there is a name for the category of all languages which are associated with total Turing machines. And I'll give you that definition. We say a language L, and unfortunately this is confusing terminology. A language L is called, the name for this is recursive, not like without the enumerable. A language L is called recursive when it is the language accepted by a total Turing machine. All right? That's called recursive. It is the language accepted by a total Turing machine. That's a Turing machine which never is going to run forever, no matter what you ask it to do. All right? So the true picture of this sort of diagram of languages, there's the regular languages, which include like the something like A to the N. There's the context-free languages, which includes something like A to the N, B to the N. The next category out is recursive. These are Turing machine languages which always halt, all right? And that would include something like A to the N, B to the N, C to the N. This is a language which we know how to write a Turing machine for that by marking. And just because we've done it already, that Turing machine, like those examples, by marking, there was no opportunity for that to run forever. It was always just going to either accept the string or get stuck at some point, some finite point. And then there's the larger category of RE. These are sometimes described as like Turing machines which might take an infinite amount of time to finish, even though I would say they just don't finish. But if you like to think about infinity, you could say these are like Turing machines which are allowed to run forever. These are Turing machines which have to actually stop and give the answer in a finite amount of time. So as far as the category which we in real life like to deal with, it's really this one. This is like the realistic category that we want to operate in. Although I will say our actual computers are actually in this category in real life, because we all know sometimes the computer will run forever. Like you're allowed, it's not hard at all to write a program in Python that will run forever, and your computer will try to do that. And so our real life computers actually are things in the RE category, but in terms of useful calculations that we actually want to do, they are in this domain, this universe, the recursive category. All right. This RE category, though, are there any individual languages out there that are even outside of the recursive, but in this RE category? There are, and we'll talk about one probably next time, because I have a few more things to say about this. You might be tempted to just say, what about A to the N, B to the N, C to the N, D to the N? That's not out here. That's also in here, because you can make a marking Turing machine that never halts to answer whether something has that format. All right. So unfortunately, like I said, I have a hard time keeping straight these two names because they are almost the same. Recursive means it always halts. Recursively enumerable means that it might run forever. I kind of remember this by thinking, like in my mind, when I think of the set of all counting numbers, 1, 2, 3, up to infinity, that set is not finite, but it is enumerable, which is to say I could just say one after another, even though I would have to say them forever to get all of them. But there is still some way to do them one after another. That's what the word enumerable means. So these ones, it's like even though they might run infinitely, there's still some kind of step-by-step process by which you would do it, but that process might have to run forever. That's what RE is supposed to mean. Recursive is the same, but without the E. That means it actually stops at some point for all inputs. All right. So the difference in terms of halting here, let me just say this is sort of a way that you could describe this in more casual language. So L is recursive. Well, let me say RE. In terms of algorithms, this means for any x, well, I should say this means there is an algorithm which accepts if and only if x is in L. All right? But I will say, and this is an important, I already wrote that once today, but this is an important parenthetical. If x is not in L, then actually you don't know what's going to happen because it will appear to run forever or it might halt. So if x is not in L, it might halt or not, and you as a user will not be able to tell the difference. That's why such a machine, if you're interested in answering this question, is x in L or not, this is actually not a very good practical machine to use in real life, okay? Whereas recursive, L is recursive, this is better. It means there is an algorithm which accepts if and only if x is in L, and halts and rejects if and only if x is not in L. All right? What that means is basically you have an algorithm which tells you yes or no. Is it in or is it not? Which is not the case in the RE category. In the RE category, you have an algorithm which says yes or maybe just doesn't say anything. And while it's not saying anything, you can't tell if the answer is going to be yes or no. But in this case, the answer always says yes or no. So the sort of recursive means we get yes, no answers. Whereas RE means we get yes answers, but if the thing is taking a long time, then you don't know what's going to happen. And so like sometimes you'll get an easy yes, but you might get a hard no answer at all, and then you don't know if the answer is going to be a yes or a no. So we get yes, but otherwise don't know. All right. And Turing realized all of this when he was creating his whole the whole thing that he was talking about. You know, he didn't call them Turing machines or whatever, but Turing immediately understood that this issue of halting or not was extremely important. And so Turing's made an example language in the RE but not recursive category, which I'll say a little bit about right now. I don't think we'll be able to get through the entire description. An example language in RE but not recursive. And this is called the halting problem, which I think I mentioned, I know I mentioned on the first day of class, maybe not since then. This is called the halting problem. And this has to do with a Turing machine which is capable of simulating another Turing machine. This is already pretty abstract, but this is what Turing had talked about, and this is something that I mentioned last time. So this is about a Turing machine which simulates another machine. So that for this Turing machine, the input is some other Turing machine and a string x. And things of that type, which ones are accepted or not? Well, here's the language. And I'm going to write this as LH. H stands for the halting problem. And this I'm going to casually refer to as the language of the halting problem. It says this is the language of all strings that look like this. M hashtag X, where M is a string description of a Turing machine, and that machine M halts with input X. All right? This is called LH, the language of the halting problem. It is the inputs consists of a description of a Turing machine followed by a string. And an input like that should be accepted if that M actually halts when you run it on X, all right? And actually, you could say accepts if you want, and it'd be more or less, it wouldn't be the same language, but it would still have the same properties.
So
Yeah.
does the hashtag just mean halts?
No, the hashtag is like a string separator on the tape. So I'm trying to write this as a string that you could actually write on the tape. So M represents a Turing machine that you have somehow encoded as a string. And then this is just a separator on the tape. And that's a legitimate string. And then you imagine running M on X. So this LH is actually, would you mind fill in the blank? This is here. It's RE, but not recursive. So I would like to try to explain, maybe we can explain the first half. So this LH is RE, but not recursive. All right. Why is it RE? So in terms of algorithms, the idea, or what this means, if I were to describe it sort of casually in terms of algorithms, is if you give me one of these, M hashtag X, I can tell you when X is accepted on M, but I might have to run for a very, very long time, all right? That's what RE means. I can tell you when M accepts X, but not recursive. That means I cannot tell you whether or not M accepts X. I can just say, yes, it does when it does, but when it doesn't, it might have to end up running forever. All right, so can we explain why LH is RE? All right, RE means if we see M hashtag X, can we say if M accepts X, right? This is something you could do in real life, and we've been doing it, we've done this many times. Like if I show you a Turing machine M, and I also show you a string, is it possible for you to tell me if that string is accepted? Yeah, you just like follow the arrows in the diagram or whatever, right? This is definitely possible to do. Can we say if M accepts X? How do you do this? You just run in terms of the algorithms, you run a simulation of this machine M and you start it running on X and you see what happens. And if it accepts, then you will find out that it accepts because accepting involves halting, all right? So can we say if M accepts X? I will say, yes, you can. Do this. Since a universal Turing machine, this is a Turing machine which is capable of simulating another Turing machine. A universal Turing machine can simulate running M with input X. And we will see if M accepts X. All right? You will not really see whether or not it accepts, because if it doesn't accept, it might run forever and you wouldn't be able to tell. But if we already know that M is going to accept X, which is, like, that's what the language is. The language consists of M's and X's, where M does halt on X. So we already know that M is going to halt on X. And so it is possible to make a Turing machine that makes that verification, all right? You can do this since a universal Turing machine can just simulate running the M. And since we've already assumed that it is going to halt, then we know that it will halt, all right? So that means that this language is in the RE category. It is not in the recursive category. And for this, maybe I think I would like to leave this for next time, just because we got 5 minutes, but it won't really do it justice for now. So can I just, maybe I'll leave it at that. Next time, LH is not recursive. That is, it is not possible, and this is the harder part in terms of what Turing demonstrated. This is the harder part, that is to say, it is not possible to make a Turing machine simulator which will not only tell you when it's accepted, but will also somehow figure out when the thing is about to run forever and like stop it from running forever and tell you this is not going to be accepted. That's a much harder thing And in fact, it is an impossible thing. That's what we'll say next time. Maybe I'll give you just for now a sort of little overview of where we're going with all this business until the end. We only have maybe 3 more class meetings. I think that's right, since we don't meet tomorrow. Anyway, you have so 2 major things that I want to cover for our remaining time together. The first thing is we have this language here, which is in the RE but not recursive category. In my opinion, and I would encourage you to talk with your friends about this at lunch. I would probably not, but what's a little unsatisfying about this is that it's super weird. Like, you can tell your friends, hey, what I learned in my Theory of Computation class is actually there are some things. So like this is the realm of like practically useful computers is out here, right? This apparently is a question which cannot be answered by a real life practically useful computer without running for infinite amount of time or something like that. All right. That's kind of interesting. There are real specific questions which cannot be answered by any real life computer. And your friends will likely say, oh yeah, what are those questions? And you'd say something about, oh, well, like if you have one computer which is simulating itself, then it can't tell if it's going to run forever or not. This is not a great explanation to your friends at the in the club. So one thing that we're going to talk about is a more down-to-earth thing. So that there are actual, real, like ordinary questions that you can also demonstrate are unsolvable by any computer, and they are questions that are not about some simulation of a Turing machine inside of a Turing machine. Like, those are very weird. Historically speaking, that's what Turing was really into, so that's the super important example. But there are actually more down-to-earth examples of uncomputable type things. And then I also want to talk about, just ever so briefly, something out here. And there are even languages out here, meaning you could not make any kind of Turing machine, even if the Turing machine was allowed to run forever on certain inputs. Their language is so weird that they cannot fit anywhere inside of this hierarchy. All right, I think maybe I'll leave it at that. This is where we're going, though.